So I'm going to talk about a graphical language for quantum computing called the ZX calculus, and more specifically about two completeness results we've had with this language. So quick disclaimer before I begin. I assume most of you do not know about the ZX calculus. So this talk will primarily focus on introducing the language, how we can use it, and also some applications of the language. I will barely even talk about the proof for the completeness. Okay. So I thought I'd start with a small introduction. So the language was introduced by Cook and Duncan in 2008. You can basically see the language as a language for quantum circuits plus post-selected measures. So it can give you a sense of what we are going to do with this language. The language stems from category theory, and the objects we are going to manipulate are string diagrams like this one. But I reassure you, you don't need to know anything about category theory in order to understand this talk. So yeah, the ZX diagrams are universal for quantum mechanics. It comes with a set of axioms, so transformations between diagrams that preserve the semantics and that can be embedded in the proof-assistant quantomatic. What I'm going to present is the ZX calculus for pure quantum mechanics, although the measure can be modeled, and there exists another version of the ZX calculus for CPMs. All right, so the ZX calculus has many applications. It goes from MBQC to error correction, verification, and circuit simplification, for instance. And also, it is a language for lattice surgery. I will briefly talk about this in the applications. Okay, so I guess most of you know what a quantum circuit is, so I'm going to start with this. A randomly generated quantum circuit. And first, I'm going to show you how to translate it into a ZX diagram. So first of all, we replace every Hadamard gate by this yellow node. Pretty easy. So then the S gate, I'm going to really express the fact that it is a rotation of angle pi over 2 around the z-axis. And so, yeah, I replace every S gate by this green node with a parameter pi over 2. And the parameter represents the rotation of the gate. Similarly, for the T gate, it's a rotation around the same axis, but this time of angle pi over 4. So it's exactly the same node, but with a different parameter. Then the X gate will be represented by a red node with angle pi in it. Then the C node gate, this is an interesting one. It's actually decomposed in ZX calculus as the composition of two three-legged nodes, as you can see. It's not, this is really one important feature of the ZX calculus is that even though its generators are not necessarily unitaries, you can then use them in order to form unitaries, like the CNOT. So here is what you get. And finally, you can see here there is an initialization for the quantum circuit. We can also translate it in ZX calculus with a red node with 0 input and 1 output. Okay. Now what you get here is really a ZX diagram. Okay, fine. But why do we want to use the ZX calculus? Why did we do all of this? Well, we remember that the CNOT was decomposed as two nodes. And this allows us to use one very important feature of the ZX calculus, which is that basically you can move things around freely. There is a paradigm, only connectivity matters, which basically says that once you've fixed the outputs and inputs of your diagram, then any graph isomorphism preserves the semantics. So you can move your nodes around as you wish. You can even transform an output as an input like this. Everything works fine. Okay. So more formally now, here are the generators of the ZX calculus. So you have green and red nodes with arbitrary number of inputs and outputs, and with a parameter. So as you can see, the green node really relates to the canonical basis, 0, 1, while the red node really relates to the diagonal basis, plus, minus. And so, in a sense, they are really equivalent just up to a change of basis. And the change of basis is given by the Hadamard node. Okay, this thing here is called the standard interpretation. It's the map that maps ZX diagrams into their interpretation as quantum evolutions. Okay, I want to briefly give you an idea of the rules of the ZX calculus. The most important one is called the spider rule. It states that whenever two nodes of the same color are connected, then you can fuse them. You can merge them, and the obtained parameter is the sum of the two parameters. So for instance, I can apply it here. Bim, it's merged. You can continue and merge these two nodes. And then you can do it recursively as long as you can. So for instance, here. And also, as I said, the green and red nodes are equivalent, so we have this rule also for the red nodes. And what we get here, we will be able to merge all these nodes here that are red, like this. Also, I forgot to mention that whenever there is no parameter in the nodes, by convention, the parameter is 0. The reason why it's 0 is that the parameter represents a rotation, and so it seems logical that by convention its rotation is 0 when there's nothing. And so when you do the spider rule on all of these nodes, you should have 2 pi at the end, but 2 pi, again, it's a rotation, it's 0. So we get this. Also here, okay. Another important rule is the color change. So, as I said, the red and green node represent the two distinct bases that are, and the change of basis is given by the Hadamard node. So whenever you have a node surrounded by Hadamard nodes, you can change its color. So you can apply it here, also here, again, at the bottom of the diagram. And also we can use the involution of the Hadamard gate in order to make this Hadamard node go through the red node, like this. And now I can use the spider rule again in order to merge nodes that are now adjacent, like this. Okay. Another important rule is the Hadamard decomposition. So we can decompose the Hadamard gate as a sequence of rotations around different axes. This is what it means here. I'm going to use, for this Hadamard gate, the following equation. I get the following result. Again, I can use the spider rule. And now I have something that I didn't have before. I have a binary node with no angle in it. So since it represents a rotation, it represents a rotation of angle 0, so it's the identity. I can get rid of this. And finally, again, use the spider rule. It's very important rule. Okay, I'm going to go quickly for the rest. What we have here is the copy rule. So this green node here represents a copy for the canonical basis. That means if I have ket0 here, which is the case, this represents ket0, then ket0 will be copied. I can apply it here. I get the following result. Again, use the spider rule, and we get the following result. Last but not least, the bi-algebra rule, which is one of the most difficult to use. It basically says, in a weird way, that the three-legged green and red nodes kind of commute. Again, in a pretty weird way, like this. So it might not be obvious, but I'll show you that I can apply it here. To do so, I will first use the spider rule, but this time from right to left, in order to split some nodes. So, oh, sorry. Yeah. So here, I'm going to use the spider rule on this node, these three nodes, in order to create something that looks like that. Okay. I still don't quite see this pattern, but all I have to do is to rearrange my nodes using the only topology matters, only connectivity matters paradigm. So here I've done really nothing. I've just rearranged my nodes. And now I see the pattern. So I can apply this rule from left to right. And I get this. Again, I can use the spider rule and the only connectivity matters rule. OK, just to show you that I can use rules from right to left and not necessarily from left to right, I can use the bi-algebra rule, but this time, so with this pattern to this pattern, for instance here, I get the following result. Again, the spider rule, I get this result. And doing so, you can create new occasions to apply the rule. For instance, I can now apply this rule here, whereas before I could not. And I won't go into the details. Here is the result after some simplifications. OK, I won't go further into the ZX rules. It's not what I'm interested in here. I'm going to talk now about the completeness. So the completeness is obtained for this language whenever two diagrams represent the same evolution, then they can be turned into one another using only the rules of ZX. That means, in order to show that two diagrams represent the same matrix, we don't have to actually compute the matrix. We can just do everything graphically. And this is important because it tells you that basically the language captures all of quantum mechanics. So it was a hard problem to tackle. So people first looked at restrictions of the language. And also, you can see that this question can also arise for quantum circuits, not only for ZX calculus. And so here are some results. I have put quantum circuits as well, just for the comparison. So you can see that we have results for both quantum circuits and ZX calculus, although the results for quantum circuits do not apply to restrictions of the language that are universal. All right, all all the restrictions for synod dihedral and above are not universal. But the one for Clifford+T is universal. And we now have a completeness result for the ZX calculus for Clifford+T. And then followed a completeness result for the unrestricted language, the language where there is no restriction on the angles. Okay, so here is a quick recap of the rules we have seen so far. I actually gave you a simplified version of the rules because I ignored some particular diagrams, like these ones. Actually, what I ignored is the scalars, because diagrams with 0 input and zero output represent matrices of 1 by 1, so scalars. And it's pretty convenient sometimes to forget about scalars. But here it is. So this set of rules has been shown to be complete for the Clifford fragment of the language by Miriam Beckens. And then we worked on this set of axioms. We added a few new rules, some of which are fairly easy, some of which are not, clearly. And we showed that this set of rules added to the previous one allowed for a complete axiomatization for the Clifford+T restriction of the language. So again, that means that if I have two diagrams of the Clifford+T restriction of the ZX calculus, I can turn them into one another using only these rules. Okay, to give you just a hint on how we prove the completeness, we noticed that this particular diagram was very, very interesting, very important, because it represents a 2x2 matrix that is not unitary, although its entries are in 0, 1. And this can be used, well, since it proved to be interesting, so we gave it a little name. We denoted it with this triangle node here. And it turns out we can use it in order to create some interesting states and operators. For instance, the W state, which is 001 plus 010 plus 100, can be represented using this subdiagram. And basically, this allowed us to create a bridge from the ZX calculus to another language called the ZW calculus, which depicts interactions between the GHZ and W states. And since the ZW calculus was complete, it allowed us basically to transport the completeness results into the ZX calculus. Also, it transpires into the axioms that this is how we got the completeness, because, for instance, one of the previous axioms, this one of the ugly ones, actually makes more sense when depicted as an equation on the triangles. So this diagram. Okay. So I'm going to go a bit quicker now. We showed that there was a natural generalization of the previous result on the completeness. So we defined what was a linear diagram. So in a linear diagram, some angles are considered as variables, whereas some others are considered as constants. And also, all the angles are combined in a linear fashion. And now we have a new definition for the completeness. Now the completeness is that we have the completeness whenever two diagrams represent the same quantum evolution for any valuation of the variables, then the ZX proves the equality between the two. And the result that was here is that for linear diagrams with constants in pi over 4, then we have a completeness result with exactly the same axioms as before. All right. So this kind of intermediate result proved to be very, very useful in order to prove the following one, which was to have a complete axiomatization, but this time for the language as a whole, with no restriction on the angles. And to do so, all we had to do was to add one axiom, which is this one. And there you go. You have a complete axiomatization for the ZX calculus. Okay, so I want to talk a bit about applications of the ZX calculus. So one possible application is protocol verification. So for instance, here you have a protocol for the quantum teleportation. This protocol can be translated as a ZX diagram, and it's pretty easy then to show that this diagram amounts to the one with just the identity between Alice and Bob. And so doing that, we can show that the quantum teleportation protocol actually works. And all of this graphically, without the use of matrices, of Hilbert spaces, and whatnot. Another example of protocol verification is superdense coding. Again, it can be translated into a ZX diagram and shown to be simply the copy of the two classical bits of Alice. All right. So another application of the ZX calculus is MBQC, measurement-based quantum computing. So first of all, graph states are easily represented in the ZX calculus. All you have to do is take all the vertices, turn them into green nodes with one output, and every edge will be an edge in this new graph with a Hadamard on it. And so, for instance, 2D cluster states will be represented like this. Also, one usual operation in MBQC is this operation of measure, and again can be translated as a ZX diagram and can be shown to be exactly what we want to perform. Okay. One of the uses of the ZX calculus can be to simplify circuits. That's something that can be of interest to you. So the protocol is fairly easy. You first start with a quantum circuit. Sorry, you turn it into a ZX diagram, just like I showed you at the beginning. Then you use the ZX calculus and its completeness in order to simplify the diagram. And then this is the hard part. You have to then re-extract a circuit from a ZX diagram. And this actually is still an open question. So in PyZX, you can, well, there is one solution that's proposed in PyZX, but I'm pretty sure it's not optimal. And this is the first two steps for a particular quantum circuit. Okay, one last application is that ZX is a language for lattice surgery. So you might have already seen talks about lattice surgery yesterday, and also some posters about lattice surgery. So what we have is we have a scheme where we use surface codes in order to encode data. And then the operations that are allowed in this surface code are, either the split or the merge. But again, there are two kinds of split and two kinds of merge, rough and smooth, respectively. And it so happens that in ZX, it can be really simply represented. And so in this case, the ZX calculus can be used as a graphical language that captures the operations allowed in lattice surgery. All right. So let's wrap things up. We have given two complete axiomatization for pure quantum mechanics for the ZX calculus. One for Clifford+T and one for the general ZX calculus, so the unrestricted language. There is a lot of applications. And also I wanted to talk briefly about some results that came after these two first results. So now we have a normal form in ZX calculus, whereas previously the proof used the third-party language ZW calculus. But now with normal forms, we can prove the completeness inside the ZX calculus itself. And it allowed us to get completeness results for other fragments of the language. It is now, well, we now have a complete axiomatization for the rationals. So again, another fragment of the language. We have a complete and easy axiomatization for mixed states and CPM, as I said in the introduction. And finally, we have now been able to simplify the axiomatization for the unrestricted ZX calculus. And this is the remaining axioms. So all you have is, well, the first three lines are the axioms for the Clifford fragment, and then you only need two additional axioms, and you get the completeness for the unrestricted ZX calculus. So I want to leave you with this picture, and thank you for your attention.
Thank you for a nice talk. Some questions here.
I have a question with regards to the simplification of the circuits. Since it's hard to extract the circuit from the simplification, yep. What's the advantage of using ZX calculus instead of just simplifying the circuit without using ZX calculus?
The point is that if we are ever if we can extract circuits from a ZX diagram, then we could use it. Well, the point of using the ZX instead of quantum circuits is that the ZX is complete, whereas you don't have this result in quantum circuits.
Can you repeat what complete means?
It means that whenever two diagrams represent the same evolution, they can be turned into one another using only the rules of the language. And so, yeah, this is really the step for which using ZX could be more appropriate than quantum circuits. Even though the third step, well, is a trade-off, basically. Yeah. Compromise.
In your axioms,
yes.
How do you reduce away measurements? I didn't see a measurement node that.
We didn't. No, there is no measurement in what I've shown. I can show you somewhere where there is a. Okay, here is one way to represent a measurement, actually, but it's not in the axioms. Indeed, the axioms are only for pure quantum mechanics with no measurement.
Yeah. Is there some lower bound for the number of axioms? I mean, my question is about optimality.
It's a good question. Actually, I don't know anything about a lower bound for this. It's a hard question because sometimes you can merge some axioms, two axioms into one. It makes a larger axiom, but still that's one less axiom. Yeah. So I don't know if it's the right metric to compute minimality. Although here we are, well, one way to ensure minimality is to at least try and check that you can't prove one axiom using the others. So that's one point. And in this axiomatization, it's conjectured that it is minimal in this sense. Actually, there are only two rules. This one and the color-swapped version of this one that are not proved to be necessary, but we conjecture they are.
I have one question. So when you did this circuit simplification in the beginning,
yes.
You made lots of choices there.
Yes.
So is there an automated way to do this? And is anything known about the complexity of this?
No, in general, for general circuits, we don't have a strategy. Well, we can infer strategies from the Clifford case, because in the Clifford case, we have a pretty simple normal form, and we have a strategy to transform any Clifford diagram into its normal form. And it can kind of be applied for other fragments. Although it's not necessarily optimal. And yeah, what I did in the beginning was completely arbitrary. It just, yeah, no, there is no, so far there is no strategy, optimal strategy for any ZX diagram.
So a related question is, can you place an upper bound on the number of moves you need to make to get from one circuit to to any equivalent circuit?
There is an upper bound, but it's pretty bad. Like it's exponential, because.
But singly exponential in what? In the number of
in the number of qubits. Because well, one way we could do this is, now we have normal forms. We can transform the two diagrams in their normal forms, and then just check if the two normal forms are equal. But in the general case, the normal form has a size of 2 to the n.
Right, but I think it has to be exponential, because if it was polynomial, then you would be able to show that two circuits were the same in NP.
Yeah.
And so that's unlikely, since it's QMA complete. To, non-identity check is QMA.
More questions?
Yeah, so I see a lot of similarities here with like tensor network notation. And in tensor network notation, it's pretty easy to write down like a linear combination of two quantum operations. So I was wondering if in the ZX calculus, you've ever thought of any sort of a sum rule for summing two ZX diagrams?
So it's not really the point of the ZX calculus to be able to write this kind of things down. What we really want to have with ZX calculus is something that's still pretty close to the quantum circuits. And so as soon as you want to do linear combinations of unitaries or linear combination of tensors, it's really far from what you can do with quantum circuits. But there are similarities, definitely, with the tensor network.
All right, last two questions.
What about noisy quantum circuits?
Okay, so yes, this is a language for ideal pure quantum mechanics. So just as for quantum circuits, you can model the noise as I don't know, a bit flip that can arise randomly, or a phase shift that arises randomly as well. So that's something you can model in the language. but it's not something you have per se directly from the language. It's something you have to model, but you can model it.
There's like mixed states and probabilistic stuff in there.
Sorry?
So there are mixed states and probabilistic.
Oh yeah, you can
elements
do
there.
mixed states. Yes.
Okay.
Yeah. There is a version of the ZX calculus for mixed states and CPM.
So you said you could use it to optimize circuits, and I was just wondering how well does that work? Like
Sorry, come again?
how big of a circuit can you optimize with the existing software?
Oh, actually, what Pi6 does. So Pi6 is this thing here. What Pi6 does is really, it's working on the graph, and so it should be polynomial in the number of operations of gates.
Really?
Yeah, but it's not.
So
optimal.
it doesn't do anything exponential. It's not like searching through a huge
No,
space.
it's
It
not-
just does some simple
Yeah,
rewrites.
what it does is just one strategy for rewriting, and this strategy really is polynomial. And then the extraction of circuits, I guess it's also polynomial from this kind of diagram. So I think it is polynomial in the number of gates. I'm not completely sure. But,
Okay.
Yeah, they already went for coffee anyway, so.
Just adding to that question, it seems to me that you cannot extract from any ZX form to circuits. Is that
Sorry,
right?
come again?
It's like this form you have for the ZX diagram. Can you extract from any ZX diagram to a quantum circuit?
No, because you are allowed in ZX diagrams operations that are not unitary. And
yeah,
so
I mean,
as-
do you know any condition that you can extract?
there has been some work done on that. How is it called again? On G-flow, using the G-flow of a graph. There is a way there is a way to have a necessary condition for a sufficient condition. Sorry, in order for a diagram to be well, in order to extract a quantum circuit from a ZX diagram.
Okay, I mean, is this online or public?
Yeah.
Or okay.
I can tell you
Okay, sure.
if you want.
What? So let's thank again to Renaud and Tamas.